Okay, there we go. So we've talked about the partition function. We beat that horse pretty good. and we'll see that it'll come back to us in a little bit, but we're going to switch gears today. We're going to talk about internal energy. We could use that partition function if we have those molecular partition functions, or even if we have like a countable number of states where we go through and generate the probabilities of population of each level. But today we're going to shift gears. We're actually going to talk about energy. That's what we were doing that whole thing for. We were learning how to calculate the partition functions so that we could get to the energies of the molecule or the particles in this quantum state. And so that's what we're focused on today, energy and heat capacity. Heat capacity is the change in energy with temperature. So it's just like Boltzmann's constant. Look at the units on Boltzmann's constant. It's joules per Kelvin, right? So if you look at the ideal gas constant, which is just Boltzmann's constant times Avogadro's number, is joules per mole per Kelvin. So you see that that's really like a conversion factor. How much energy can I put into a system before it changes temperature by 1 degree? It's a slope. If I change the temperature, how much does the energy go up? Okay. And so we're getting into this area called statistical thermodynamics. So the Boltzmann distribution of microstates is really what we use to describe thermal equilibrium, and that gives us that partition function. And this connects quantum theory with bulk properties. So this was really the thing that caused scientists to believe quantum mechanics. So they had spectroscopic experiments like the black body radiation problem, or the photoelectric effect, or the line spectrum of a hydrogen atom. And they used quantum mechanics to explain those, but was that just a sort of an ad hoc theory, like it only worked for spectroscopy? And so, I mean, to say that all of nature is quantized, just so you can solve the hydrogen atom spectrum, that might just be sort of a mathematical trick. That nature may not actually be quantized, it's just that kind of theory works only for spectroscopy. So a lot of the scientists who were thermodynamics specialists were very skeptical. But as they used Boltzmann's distribution, they were able to then derive entropy and derive enthalpy and derive all of these different energy. And that's what statistical thermodynamics is. It's its own course in graduate school. So if you take thermodynamics, you don't start where we started in this course. I've kind of combined those two topics. Thermodynamics, you start with the first law of conservation of energy, and you work your way through the second law and defining entropy and so on. We're going to jump into that right after the first exam. So I went ahead and took that quantum or statistical thermodynamics piece and put it in here in front of the traditional thermodynamics so that you could see the connection of the fall semester to thermodynamics. And this is what really convinced those people that quantum theory really was underneath all of nature. So we can get to all of these energy terms, like the enthalpy, the heat capacity, Helmholtz free energy, which is given the letter A, and Gibbs free energy, which is G. And we can even get the equilibrium constant, K. So this even governs all of our equilibria. So it's a very robust theory. And so this is what we're going to do today, is the heat capacity and the internal energy. So we calculated this Q here, and we used the Boltzmann distribution pieces of these Boltzmann factors to do it. So we're very well versed in these two pieces of this problem, right? This comes from the energy level diagram, right? So we need to know what those energies are in order to calculate the internal energy of the system. But this is a decision point. If you have a problem that says things like a 3-level system with energy spacing X or whatever, then you use this equation to determine the internal energy. If it says like a molecule or a mole of argon gas or something like that, then you're dealing with 6 times 10 to the 23rd particles, and you've got a complicated system. It's an atom flowing around in space. You've got billions and billions of energy levels. You can't use this because this is a sum across the energy levels. So you're not going to be able to do a discrete sum on a problem like argon or water at 1 atmosphere. You're only going to do this in problems that have a countable number of energy levels. And so that's what I'm saying here. Only if you can count the number of energy levels would you use this kind of equation. I put this special slide in just to emphasize, because a lot of times the students will get confused, calculate the internal energy. Well, which equation do I use? I've got all these equations that allow me to calculate the internal energy. And so I have to tell you, sort of like a flow diagram, if you can count the number of energy levels, like you got a 5-level system, it's tedious, you got to do 5 levels, but you could do that. And I'd want to get into Excel and just crank it out in Excel, okay? So that sum of all of those energies times each quantum state, these are probabilities here. So what we're really saying is the energy of state I times its probability. And that kind of makes sense. That's an epsilon. This is the sum. Okay. So we're just saying, okay, I've got the ground state. What's the probability of being in the ground state? And add that to the next excited state times the probability of being in that state. So it's just like a weighted average of all the energies. And then you add them all up. And then from U and Q, you can get all these other thermodynamic properties. So these equations definitely need to be on your note card. You use them in all of your problems. And I just call it USHAG. Okay. So that's a series of calculations that you can do, and you'll see that on the homework. Calculate internal energy, then the entropy, then this, enthalpy, and all of these different things. And notice it is all rests upon U and upon Q. And really, U depends upon Q. So that's why the partition function was so important in that Boltzmann distribution. So we calculate the Boltzmann factors, and we calculate Q, then we use that and the energies to get U. Then we can use Q here and U here to get the entropy. And then we can use U and the temperature of the system to get the enthalpy. And notice these are not deltas. These are the actual enthalpy of the system. And then if you have a reacting system, you can do a delta H and delta G, products minus reactants. Okay. And then once we have the enthalpy, then we can take the entropy and the enthalpy and combine those and get the Gibbs energy. And then with the Gibbs energy, we can take delta G for reaction and calculate the equilibrium constant. So it's USHAG and then K is that extra piece. So that's the next 3 lectures. We're going to go through and calculate these quantities for a bunch of different systems. So today we're starting with the top equation, the U equation, and then we'll add in heat capacity. So at high temperatures, the translational, rotational, vibrational energies are greatly simplified. And so this U translation just becomes this 3/2 nRT. So you see it's directly proportional to the temperature. And where's this 3/2 come from? Well, it's 3 degrees of freedom, and you have a 1/2 of a unit of R for each of those. And then it's always times the number of moles. So if you had 20 moles, you'd multiply the whole thing by 20. So the individual differences in the molecule, especially in translation, don't mean anything. It's just the whole mass of the particle translating around in space. Okay. And then for rotation, we also have 3/2 nR, and that's 3 degrees of freedom, 1 for each rotation. Now remember, we have differing numbers of rotations, and so nonlinear molecules, I should say, linear ones only have 2. So linear molecules would be 2/2 instead of 3/2. And then for vibrations, we have one of these for every one of the active vibrations. So the vibrations become active at 10 times that rotational or vibrational temperature. And so we have 3n minus 6 potential vibrations, but often only about a third or a half of those are activated in bigger molecules. In smaller molecules like water, ammonia, and so on, none of them are activated. And so we wouldn't see any vibrational contribution to the internal energy. So this is so easy, right? We don't have to calculate the partition function. We don't have to calculate there's no energy level diagram because this is at high temperatures. We have 10 to the 30 energy levels populated. So there's no easily drawn energy level diagram. There's 10 to the 30 of them. So it's all smeared out, and we just have particles flying through space and rotating, and this is the energy we get from all those different pieces. And so this is a decision point. Use these formulas when dealing with moles of particles, or if you see the word equipartition in the problem. I'm sad they're not requiring the GRE anymore for graduate school, but these would be some of the questions on the subject exam. You take the chemistry subject exam for the graduate record examination, and then there would be an equipartition problem on there almost every time, because it sounds really difficult. You get all of this internal energy and everything like that, but the calculation is super easy, right? So it's really a vocabulary problem. If you can understand the vocabulary, you can remember 3/2 are, or 3/2, yeah. So it's a very simple, fast calculation, but it's more like a vocabulary, thermodynamics vocabulary calculation. Okay. So thermal excitation, of course, to the electronic energy levels, we covered that last time. It's almost never considered. So there's no internal energy component due to the electronic state, because remember, at high temperature limit, thermal excitation would start populating antibonding orbitals, and we would change the molecule, and it would break apart or completely decompose. So we're not worried about U electronic. We have U translation, U rotation, and U vibration, but no U electronic. So let's look at some of the calculations. If we look at the definition, this is the thermodynamic definition of heat capacity right here. So the heat capacity at constant volume. So if we have this substance in a constant volume container, then the heat capacity is the slope of the energy with respect to temperature. So that's one of the simplest derivatives you'll ever do. Right? So here's T. It's with respect to T, we take the derivative of that. We just have 3/2 nR. So that's our heat capacity for the translation. It's going to be the same for rotation. Okay. And this would be for linear, and this would be for nonlinear. So 2/2 R for linear, 3/2 R for nonlinear. The reason I'm saying 2/2 R for linear instead of getting rid of the 2/2 is because we're going to have a lot of halves added together. And so we just keep it that way. Plus it emphasizes that there's 2 versus 3. So 2 for linear and 3 for nonlinear. And it keeps it from being confused with the vibration, which doesn't have any halves things in it. And so then the vibration is just, I put an A in here just to emphasize it's the number of active vibrations. So we'll see that A in a little bit. So A is the number of active modes. When the temperature gets above 10 times the vibrational temperature, that mode becomes active. And then the total heat capacity is the sum of all of these things. So transrho vibe, notice there's no electronic. Again, we're not going to be storing thermal energy and electronic energy levels because they're so far apart. And does everybody understand what I'm saying about the heat capacity? I keep using the word storage. So as I heat something up, I'm putting energy into it. The temperature is going to rise. How much energy can I store in that substance before the temperature goes up 1 degree? Like you can think about water, right? If I have liquid water, I can put a lot of energy into it, but eventually it starts to boil and it's no longer liquid water. How much energy can I store in that substance before it boils? When it reaches 100 C, it's going to boil. So this is what we're talking about. How much energy can I put in that substance before a phase change or what have you? So really this heat capacity, that's what that word capacity is telling us. It's the capacity to store heat before the temperature changes. And just by comparison, because I just recently did this comparison for another talk, and that was water has a heat capacity that's about 7 times more than stainless steel. So I can store 7 times more energy in water for a given degree than I can in stainless steel. That means stainless steel is going to heat up a lot faster. It's also going to cool down a lot faster. That's why we make our heat sinks out of metal. They transfer heat very well, and they cool down really fast. Okay. We also can transfer heat from point A to point B using water because it can flow. So we use water cooling in our automobiles to steal heat away from the engine, so we can flow that around to the radiator and heat that metal up, which is easily cooled by the air that flies by it. So all of these things we use in engineering the products that we use every day. So let's practice a little bit. So here's our equipartition theorem. Go ahead and write these guys out in your notes, and we'll do a Kahoot, and we'll quickly try to put these into action. Okay. And this will test to see if you've got the basic concepts. Okay. Okay. Let me try to get the correct one on here. No. Yeah, that's it. All right, here we go. There's our music. There we go. You're gonna have the music on. All right, welcome everybody. Got to be quick today. That's why I got the candy. All right. What's the room temperature heat capacity for a mole of helium? 1 mole of helium. So think about helium, what it's doing, and what it can do. And we're talking about heat capacity. So that helps you decide between a couple of these. All right, so it's this one. So what can helium do? It can only translate. And so for the 3 different types of motions, it's not going to have any vibrations. It's not going to have any rotations. So it's only translation. And it's going to be R, not RT, because this would be the energy, but this would be the heat capacity. Okay. All right. Question 2, what is the heat capacity for 4 moles of helium at room temperature? 4 moles of helium at room temperature. Okay, yeah, so it'd be 6 R's. Basically, you're multiplying the 3 halves times 4. Okay, so it'd be 2 times 3 or 6. Okay. What is the heat capacity for 1 mole of carbon monoxide at room temperature? 1 mole of carbon monoxide. Yeah, okay. Trying to see if I can do it in my head. No, 3. Yeah, okay. Got it. Waiting us out, huh? There we go. All right. So was that the last person who waited until they got to the end? So explain what's going on here. How did we get to 5 halves?
3 halves plus 3 halves.
Yeah, so we have 3 halves for translation. So pretty much all of the molecules and atoms, we're only dealing with gas phase. And so I should really emphasize that. These equipartition theorem, heat capacities and energies, we don't have a good way to calculate them for liquids and solids. So we're going to stick with gases. Okay, so they're all translating. Some of them are rotating. If they have 2 or more atoms, they can rotate. If it's helium, it's not going to rotate. There's no way to know it's rotating. And then if it has really low frequency vibrations, some of those vibrations will vibrate. Okay. So it'd be 3 halves plus 2 halves was 5 halves because it was a linear molecule. Okay. What is the heat capacity at constant volume for 1 mole of water at room temperature? And remember, at room temperature, we don't have enough, I'm giving you a hint, to vibrate. We can't. The bending mode is 1,500 wave numbers. We're not at 10 times that. We're at 200 wave numbers, and its bending mode is 1,500 wave numbers. So we would need to be at 10 times that. So we would need to be at 15,000 wave numbers to activate that mode, which is in the visible region. Okay, that's good. All right, so 3 halves for translation, 3 halves for rotation. It's a nonlinear molecule, so we have 3 halves for the rotation, and none for the vibration because we're at room temperature. Okay, so let's see what we've got next. A little shake up. Got a streak going. All right, what's the maximum for water? So let's just now take into account all of those vibrations. How many would we have with the translation, the rotation, and then all of the vibrations? All right, very good. So it's 3 halves for translation, 3 halves for rotation. That, gives you 3 R's, and then there's 3 vibrations, so 3 more R's. So that's 6. Okay. All right, so what do we do? Creepy skeleton. It's like Halloween or something. And then a cat with an apple pie on his head. And then the one-eyed globe. Way to go. One-eyed globe. That's great. It's always enjoyable. So we'll actually put some real numbers to it here at the end of the lecture. I've added some problems at the end. So this is just showing you graphically what we have in terms of the heat capacity as a function of temperature. And so if we've got a diatomic molecule, at really, really low temperatures, this is the thing that Einstein won Well, I don't. I'm trying to think. Anyway, he wrote this paper like in 1 month. He showed that this heat capacity goes down to 0 as temperature goes to 0. Oh, come on. Yeah. I can't do 0 down here because it's running into the little tool area, but this would be 0 down here. Okay. They had observed, that was the fourth thing that where classical physics failed. They had classical physics was giving us these translational partition functions. I think somebody's moving the table or something. And they, these values, experimental values went to this to this classical value of translational energy and translational heat capacity. But then they noticed for certain substances with really rigid structures like diamond, they would drop off as temperature went low. And so the heat capacity for diamond was one of the ones that caused physicists to question what's happening. Why is the heat capacity falling below 3/2? And then Einstein showed if we just model it with a simple oscillator, basically using Boltzmann's distribution, we can show that it goes to 0 as temperature goes to 0. So he solved that using statistical thermodynamics. But if we go up at a certain temperature, we begin to populate all of those translations. So this is the translational heat capacity. Then we get above that rotational temperature. It runs up to 5/2. Then when we really heat it up, we get to the vibrational area, we start to get, this is for a diatomic, and so we get another 2/2, another unit of R for the vibrational, and then we keep going, it dissociates. But when it dissociates, it's a diatomic, so it goes to 2 atoms. And so 2 atoms translating, that would be 3/2 for atom 1 and 3/2 for atom 2. And so now we've gone from 1 mole of a substance to 2 moles of a substance. So when it splits apart, we now have 3/2 in R, but N is equal to 2 instead of 1. So anyway, that's just showing you the temperature dependence of heat capacity. And it's just reminding you that we don't have electronic. It doesn't keep going up to electronic areas, because as it starts to go up here, we start populating antibonding orbitals and we split the molecule apart. Let's look at some of the data from the CRC. So this is actual measured values of heat capacities. So there's a lot on the table, so let's break it into pieces. So we can see up here for these are for gaseous argon and gaseous copper and gaseous mercury. So this is above their boiling points or vapor pressure above their liquid. These are the heat capacities of those vapors. And so look how almost perfect they are. And here's our theory, 3/2 R. If we calculate 3/2 times the gas constant, we get 12.472. So this is the theoretical values here in the middle. So this using this equipartition, we get these things here. And since those are just monatomic gases, this would be all we have is 3/2 R. Then we get to aluminum. Okay. When we get to these diatomics, like bromine, carbon dioxide, carbon disulfide, or linear molecules, we have 3/2 R for translation, 2/2 R for rotation. And so here's our new theoretical heat capacities. So here it's pretty close. We have 27 is the actual and 20 is the theoretical. Look at aluminum and uranium. Aluminum comes in at 13, so it's a little bit above 12. It's an atom, so what on earth could be going on with aluminum? It can't vibrate, it can't rotate. So what thermally could be going on with aluminum? And just look at the others, how they really nailed the theoretical value. So this is definitely something going on. something happening with aluminum.
Is it the electron at sea level?
That's the only thing we have to point to, isn't it? So we have an electron. It has a choice of being in the p orbitals, px, py, pz. Okay, it can be spin up with those and spin down, and so one of those. Remember from our term symbols, we have all these little hyperfine states, depending upon whether the spin is with the spin of the orbit or against the spin of the orbit. So spin orbit coupling. Those are really closely spaced energy levels, and so because they're closely spaced, they can accept thermal energy. So you could excite that aluminum slightly by changing its spin orbit coupling, going to an excited electronic state. So even though I said we don't have any thermal impact of electronic states, in some rare situations, like spin orbit coupling and so on, we have really closely spaced energy levels. And so, yeah, for 99% of the cases, we don't have thermal storage of energy into electronic states, but if those electronic states are close enough, then their spacing is on the order of 200 wave numbers or less, then we can start putting energy into those. Again, it's all depending upon the energy spacing and the amount of thermal energy you have. So if we have 200 wave numbers of energy at room temperature, and our energy level spacing in some atom like aluminum is below that, then yeah, you're going to have thermal excitation of some of those spin orbit states. And uranium, same kind of thing. Particle in a box, right? It's got its translational, the whole atom moving around, but think about the electrons in the huge atom. Okay, so lower down here, uranium is down in the F block over here on this side, and it's not even in the F4, it's in the F5, the 5F orbitals. Those are really far away. Do you remember my analogy that it's that red ball in front of target, which is about a meter in diameter, was the proton, how the 1s electron would be in Madisonville or Spring or Lake Livingston, or all the way up, all the way over to Navasota. So that would be the hydrogen atom. The sodium, where was the 1s electron, the 3s electron in sodium? It was in Argentina. And so, again, then the energy level spacings of the electron that far from the nucleus are going to be really close together. And so that's probably what's happening in uranium too. It's these microstates of the electron being in the 5F whatever, or maybe it gets bumped up into the 7S, or the 3, 4, 5, 6, or the 7D. The difference, energy difference between a 7D and an 8S and a 5F are going to be really small. If those energy differences are under 200 wave numbers in energy difference, then yeah, we could populate those at room temperature. And so we would see a higher heat capacity than just the translation of the whole atom of uranium. It's mostly the translation of the uranium atom because it's very close to 12.47. So that's 3/2 R. But then where's this extra bit of heat capacity come? This comes, again, we can have capacity to store a little bit of heat in those electronic states too. Let's look at the bromine and so on. Now here we're dealing with the big atoms. So the vibrational frequencies for the bromine are actually being slightly activated. And so we're able to store a little bit of heat in the vibrations of the bromine. It's mostly rotation and translation. We see that because it's very close to 20. It's 27. Okay. Carbon dioxide is 28. Carbon disulfide is 37. So notice how the heavier atoms, those sulfurs, that's going to be a lower vibrational frequency, which means we're more likely to be able to store energy in those lower frequency vibrations. Then we have water and ammonia and all of these here. And then this trinitrotoluene fluoride, as I was going through the table, I saw that. and it said NSF, and I was like, there's a molecule called NSF, nitrosyl fluoride. But actually, the structure, the nitrogen's in the middle, right? So it's really F and S is the molecule. But anyway, I just included that because that blew my mind as I'm going through the table and saw NSF as a molecule name. So anyway, I put that in there. And anyway, these are showing some translation rotation. Water is very close to its classical value because those vibrations of the hydrogens are really high in energy. So we're not storing any energy in those vibrations, maybe 4%. But then as the atoms get heavier, we're able to store or activate more of those vibrations. Notice the theoretical for all of these is just the translation and the rotation. But what's missing is the vibrational piece. So this is why I'm saying it's 25 for all of these. But notice how they range. I mean, water's 25, but it goes up to, for C60, 504. So I thought, well, let's calculate the difference, and let's see how many units of R is in that difference. And so here for these top two, they don't have any vibrations, but like for bromine, CO2, CS2, this is the difference. And so this is about 80% of one vibration being active. Now, what does it mean to activate 80% of a vibration, right? It's either excited or it's not. And so this is a way to think about 80% of those molecules are excited and 20% are not. So remember, we have, these in different populations, and for vibrational levels, we definitely have this countable number of states. And so we have, you could say that roughly 83% of those bromine atoms are in the excited states and 20% are in the ground state. This is one way to think about it. What about CO2? Now we're talking about one whole vibration. This has got 3 atoms, and so there's, and it's linear, so there's 4 vibrations. 2 of them are degenerate. Okay, so it's got 4 vibrations, but one of them is almost completely active. So one of the 4 vibrations in that molecule is active. You could say that, or 24% of the molecules in that box have vibrational excitation. That's another way to say it. And then for CS2, we've got heavier atoms, and so we've got more populated vibrational limits. Now let's get into the larger molecules. Look at water, very close to its classical value, so only 1% of those water molecules have any vibrational excitation. But then we get down here to these bigger molecules like benzene, 20% are excited in the vibrational levels, and then C60, 33%. So do you see how vibrations are really the flexibility between the different substances? Think about in qualitative organic analysis. You take a substance, you take an FTIR of it, right? That fingerprint region is called the fingerprint region because that's how the atoms are all bonded together. That's also what gives each substance a different heat capacity. Because how that molecule is bonded together is the real difference between substance A and substance B, and that's going to give them a different heat capacity in the way they behave. Now, I didn't catch this until this year, and I've been a scientist I've been out of college for 30 years. Okay, it's quite a while. And it's kind of neat to have learned something just recently, that you'd seen in front of you the whole time, but never really picked up on. And that is, this heat capacity is a way to capture the molar mass of a substance. And that's what they used. That's why they knew about heat capacity in the 1700s, is once they determined that if I know how many joules I put into a substance, and you can do that with a heating bath or what have you, stick it set the substance into an area where you can measure the heat that flows into the substance, and then you measure the temperature. The slope of that curve is the heat capacity, and it depends upon moles. It's R, which is joules per mole per degree Kelvin. Now, if I weigh that substance and put it in there, I know the mass. And my measurement depends on moles. You see the cool thing there? I know how much mass I put in. My measurement depends on moles. I know how much a mole weighs. So that was what they were using this heat capacity for, was to determine molecular weights back in the old days. And then that's why they discovered this problem with diamond and some other substances. So they were like, wow, we cool this down and the heat capacity doesn't behave like its classical value. So it's kind of a crude way to measure molar masses. Now we throw it into a mass spec, much more precise and more accurate. Okay. And so this is the whole thing is calculated by Gaussian. You have the classical translation and rotation, and then you have all of these pieces with the heat capacity for vibrations. And so you could put all of those different temperatures in, and you could get it for every one of the vibrations and come up with the theoretical value for the heat capacities. So these are coming soon. These calculations are very important for heat engines, because we're dealing with a gas. Now, what's a heat engine? We heat up a gas, it pushes on a piston or spins a rotor or something like that, turns a fan blade. So these are called working fluids. And we're going to measure the heat into that fluid and how much energy we get out, the work that comes out, the heat that's lost, and so on. And so this heat capacity is an incredibly important piece of that puzzle. So you really have to be good at these theoretical values for heat capacity. So let's do 3 quick example problems. So if you have a blank sheet of paper, we'll do some quick problems. So what's the constant volume heat capacity for C60 if 33% of its vibrations are active at the given temperature? So it's a confusing sounding problem, but you can work its way through. Okay. So what's your first piece? Again, we're dealing with gases. So just like in the Kahoot, what did we do for a gas? The first one was translation. So we know we have 3/2 R for that. So go ahead and multiply that out. I've done it for you, but 3/2 R is 3/2 times 8.3145 joules per mole Kelvin. So it's 12.472 joules per mole Kelvin. This is C60. It's not a linear molecule, right? So there'll be 3/2 R for rotation. So that's also another 12.472. And then for vibration, we have the number of active modes times R, right? And I'm telling you that there's 33% of the modes in C60 are active. So how many vibrational modes are there in C60? Well, there's 60 atoms. So 3 times 60 minus 6, which is 174. And I'm taking a third of that. So a third of 174 are active, so that's 58 vibrational modes are active. And I just multiply that 58 times the gas constant, and I get 482 joules per mole Kelvin. So that's the vibrational piece. That's the whole ball, flexing. The individual carbon-carbon stretch, probably not active. But the ball, changing in its dimensions, squishing, all the different ways you could squish a ball, those are the vibrational modes that are active. And so this, you just add them all up. Translation, rotation, vibration, and you get 507.19. And our literature value from the CRC was 503.69, so pretty close. Since we only have 1 minute left, I've got 2 more similar problems. I'll just talk through them. So just watch, and then you can go to the video and check those. That way, when you're looking down, you won't notice what I'm talking about. So what is the constant volume heat capacity for 10 moles of argon? So now we throw in a number of moles in there. So argon can only translate. So there's no rotation because it's an atomic gas. There's no vibration because it's an atomic gas. And so we have that value, it's 12 joules per mole Kelvin. And so we're just looking at the units. I know I just multiply them by that by the number of moles I have. And so 10 of those would be 124.72. And look at the units now. After I've taken into account the number of moles, it's just joules per Kelvin. Okay. So I put in so many joules, and I get a certain temperature rise. This also tells me if I have a certain temperature, that's how much energy I have stored in that substance. Okay, there's our literature value. Then we could do 10 moles of water, room temperature. So we have the translation, we have the rotation, but we don't have any, at room temperature, we don't have any vibrations that are excited. So it's just translation and rotation. We have 10 moles of that. And so it's 10 times that 25 or 250 joules per Kelvin. All right, so you feel comfortable now with heat capacity? Good. Okay, so we'll continue on next time.